So, so the iris dataset is a dataset about three types of irises, three types of flowers. So we have iris versicolor, setosa, and virginica. So these are the three classes. So this is a multi-class classification problem. And then our data looks like this. Our data looks like this. These are our features. There are four measurements that we have for each flower, because each flower has a petal and a sepal. And then for petal, we can measure the width or length. And for sepal, again, we can measure the width or length. That's how we have four features, right? So for example, for this flower, the sepal length is 5.1 centimeters. Sepal width is 3.5 centimeters. So these are just the measurements, and it belongs to the species Setosa. So the idea is using these to train a KNN classifier, so that if we have a flower that we don't know what type it belongs to, we just check what are the other flowers in the data set with that sort of range of values for sepal and petal. Then based on the flowers that are closest to it in the geometric sense, we classify and say this is a versicolor, right? Oh yeah, everything is iris here. In this data set, we only have three types of irises. So the only classes are setosa, versicolor, and virginica. Yeah. So the question is just deciding between these three. We know that everything in this data set and also everything in the test set is iris. Okay, so here I'm just loading the iris data set. It looks like this. This is exactly the first row of the data. You can see that feature number 1 is 5.1, feature number 2, feature 3, feature 4. So, and the classes are coded separately here. All these 50 rows of the data are setosa, and they are coded as 0. Then these 50 flowers are versicolor, and they are coded as 1. And these are coded as 2, they are virginica. So this machine learning system is supposed to take in those four measurements and then either return 0 or 1 or 2. So here, let's say, I just want to use two of the features, feature at index 2 and feature at index 3. So I'm selecting these two columns of the data, call it X, selecting the targets, call them Y. Then in KNN, the idea is that we make predictions on every single data point in that range. So you can see that this background shading actually represents predictions. So every single data point in here is something that we try with this classifier. And this becomes yellow because the first nearest neighbor to this point is yellow. That neighbor is this one, right? You might be wondering why this one is yellow. The prediction is yellow here because the neighborhood, the first neighbor that it has is this yellow thing. You might be wondering why we are indifferent here. This is because when we try to get one neighbor, we send out this neighborhood and we collect this and this at the same time. And that's why it's a tie. So also in the code, I'm creating some kind of mesh, some sort of background of all the data points, and I make predictions on them. First, I'm going to just fit to the data using a 5 nearest neighbors classifier. So K is 5. It is fit to the data. Now I can just make predictions on every single data point in that range of values. And then when we look at the plot, it looks like this. So on this plot, on the horizontal axis, we have one of the features. And on the vertical axis, we have another feature, right? So you can see that get these 3 regions, right? So the background shading, it's for coding, right? So you should only use your laptops if you're following the code. So if it is for something else, you need to put your laptop away. So we get these 3 regions, as you can see. This region is purple because for all the data points in this region, the closest 5 neighbors are some of these purple, circles. Then we get this region, and then this 3rd region. And you can see that there are some points where the color of the point doesn't match with the background color. This means that, for example, here, this flower is indeed yellow, class yellow, but if we want to make a prediction for it, the prediction would be blue, because all the predictions are based on the background shading, right? That's why this is one misclassification. This is a 2nd misclassification, this is a 3rd misclassification, and this is a 4th misclassification. So that's why our misclassification error rate is 4 out of 150. Or our accuracy is 146 out of 150. And both of these measurements are on the training set. So we are evaluating the model on things it has seen before. It would have been easy for it to just memorize everything and be correct on all of them. That would be one nearest neighbor classifier. But this wasn't the case. So the thing is, the fact that this error is not 0 is actually a good sign, a promising sign for us. We don't want this to be 0. Right, so now about normalization and what goes wrong if one of our features has like fractional values, the other feature has like 1-digit values. I'm changing the units of these measurements. For one of them, I'm changing it from centimeters to meters by dividing the numbers by 100. Then my features would look like this. You can see that, maybe it's easier like this. You can see that this feature, these are still in centimeters, but for this column, I converted everything to meters. So now something that was 0.2 centimeters is now 0.002 meters, right? And now the issue is that the distance will be more impacted by the values in this feature compared to the values in this feature. Does it make sense? So in terms of this 2nd column, pretty much all the data points are, some tiny number, 10 to the power of minus 3. So they don't really matter, because when you add and subtract those numbers, you get some tiny number that compared to the difference between 1.4 and 1.3, that difference is 2 orders of magnitude smaller. So now if I use the same KNN you can see that the decision boundaries are now almost vertical. This is because this K&N classifier is disregarding petal width, which is now in meters. Because petal width for all the data points is just some tiny number. It's almost 0. And their differences is also very tiny. That's why the decision boundaries are almost vertical. And this is not a good model. Sorry, this is not a good classifier. So the thing is, this is not just about units of measurement. So sometimes the units of measurements are the same. Both of them are in centimeters or millimeters, whatever. But they are just referring to two things that have different range of values or different magnitudes of value. Just consider dimensions of this. Here, I guess the dimension is like 4 millimeters or something. This one in millimeters is is like 100, right? It's like 10 centimeters, right? So this is 4, a one-digit number. This is 100, a three-digit number, right? So if you have a data set on, measurements of different pens, this measurement is always a one-digit number in centimeters, and this measurement is a three-digit number. And that's an issue if you want to measure distances, because the distance will be dominated by the feature that has higher magnitude. So that's why we have normalization, which takes care of all these inconsistencies for us. So now what I'm going to do is to first convert one of the features from centimeters to millimeters, just to mess up the data set even more. And then I'm going to use normalization. So normalization, usually we just use scalar.fit to normalize the data. We must do this if we are using K&N. K means support vector machines or any other model that has distance in it. So we normalize the data. Now on the normalized data, I'm fitting the model and plotting it. The model now looks like this. You can see that the boundaries are somewhat tilted, which means that the impact of the both features were possible. They made whatever impact they needed to make on the classifier. It is not like one of the measurements is dominating the predictions. So this is good. The error rate actually didn't change that much. I can see that here it's, maybe it's 3. Yeah, but this is error rate on training data, so we don't really care that much about it. But the error rate might also change a bit. But what matters here is that you can see that here the range is from -3 to 3. And also for this measurement is again -3 to 3. So these are z-score values. So they are not really measurements. When we say, petal width is -3, well, it's a measurement. How can it be -3? It's not -3 centimeters. What this means is that petal width was 3 standard deviations smaller than the mean of that distribution. If height of a person is -3 z-score, it means their height is 3 standard deviations below the average height of that population. So, now you can, if you look at the range of the values before and after normalization, you can see that before normalization, we had these blue ranges. So for feature number 2, the range was maybe from 1 to 5. For feature number 3, the range was from 5 to 20, right? And then after normalization, the range for both of them is -3 to 3. So that's how normalization takes care of differences in units and differences in magnitudes of the feature.